So the first speaker is Sofia Pinheiro. She's from the Department of Mathematics from the University of Aveiro. And she's going to talk about, so her talk is about graph spectra, and it is the adjoint of arbitrary families of graphs. So one more thing, if the participants want to ask some questions, there is below Q&A, so you can ask there. So you can start, Sophia.
Okay, thank you. Good afternoon. First of all, I want to thank Inid and Raquel for the invitation. And now I will present you a joint work with Professor Domingos Cardoso and Helena Gomes, that is the adjoint of arbitrary families of graphs. First, I will define the adjoint graph. For that, consider a graph H with vertices 1 to P and a family of graphs with graphs G1 to GP. The adjoint of this family of graphs, also called the generalized composition, is this graph, where the vertices are the vertices of G1, G2, GP, and its edges are the edges of these graphs, G1 to GP, and there is an edge between a vertex of GR and a vertex of GS in the join if the edge RS is an edge of the graph H. For example, considering H a path P3 and the family of graphs G1, G2, G3 as the complete bipartite graph K13, the complete graph K2 and the path P3, then we have this P3 join. That is a graph with 9 vertices, and these edges are here, and also vertices 5 and 6 are linked to all vertices here and here. Okay, this is then the P3 join graph of this family of graphs. In this work, we deal with the universal adjacency matrix of a graph, in particular with the universal adjacency matrix of the adjoint. The universal adjacency matrix of a graph is denoted by U of G, and this matrix, where A of G is the adjacency matrix of G, N is the identity matrix of order N, N is the matrix with all entries equal to 1, and this D of J is the diagonal matrix of the graph G. This alpha, beta, gamma, and delta are all scalars. In particular, if we consider the adjoint graph of a family of arbitrary graphs, according to Saravanan, we have the universal adjacency matrix given by this matrix with these entries, where this Wi is given by the sum of the order Nj when J is a neighbor of I in H. Okay, and also this delta 1, 2, delta, in fact, delta Ij is equal to 1 if Ij is an edge of H, of the graph H, and 0 otherwise. From now on, let us consider this matrix UI, that is the sum of the universal adjacency matrix of GI and this delta Wi and this identity matrix. With this, we may conclude that lambda is an eigenvalue of the universal adjacency matrix if and only if this lambda plus delta Wi is an eigenvalue of UI. Extending the concept of a walk matrix of a graph to its universal matrix denoted by U, we obtain this walk matrix WU with these column vectors such that this the number of columns k is the maximum number for which its columns are linearly independent. In particular, for each UI, we have this walk matrix given by these column vectors. If this SI main eigenvalues of the matrix UI, then we have the main characteristic polynomial of the matrix UI, that is this polynomial of degree Si. With this, we proved this equality. In fact, this generalized a similar result involving the adjacency matrix, and this equality allows us to conclude that we have this equality, that is the product of the walk matrix of each UI and the column vector where the entries are the coefficients of the main characteristic polynomial is equal to this, to the UI power Si and times the all one vector of order Ni. This allows us to conclude that the coefficients of the main characteristic polynomial can be determined solving this linear system that has an unique solution. We also proved that the number Si of main eigenvalues of UI is equal to the number Ki of columns of the matrix WUI, that is the walk matrix of UI. As a consequence, the main subspace of UI is spanned by the column vectors that are in the walk matrix of UI. Now, let me introduce the edge-join associated matrix. For that, I already said that delta Ij is equal to 1 if Ij is an edge of H and 0 otherwise. And so the edge-join associated matrix is a matrix of order S, where S is the total number of main eigenvalues and is denoted by W tilde and have as these entries. This matrix in the principal diagonal, this one, is the matrix with these entries, where the last one have entries equal to the coefficients of the main polynomial, main characteristic polynomial. These matrices are the companion matrices of the main characteristics polynomial for MUI. And the matrices M21, P1, M12, and so on, that is these matrices have these entries. The first column is this one, and the entries in the remaining rows are equal to 0. Now, this theorem is the main result of this work and establishes an expression for the entire spectrum of the universal adjacency matrix of the edge-join of a family of arbitrary graphs in terms of its components and also in terms of the spectrum of the H-join associated matrix W tilde. As a consequence of this theorem, we can see this equality, that is the characteristic polynomial of the universal adjacency matrix can be determined using the characteristic polynomial of each UI, the main characteristic polynomial of each UI, and in terms of the characteristic polynomial of the H-join associated matrix W tilde. Let me give you an example. If we consider the graphs as in the beginning, we will determine the characteristic polynomial of the universal adjacency matrix, considering the scalars alpha, beta, gamma, and delta all equal to 1. Recall that for this, we need to calculate this. Okay. Okay. I will explain in more detail this first computation, because this that involves the universal adjacency matrix of G1, yes, and because the other ones are similar to these computations. So we have to compute UI1, that is the walk matrix of the walk matrix of U1. Then this matrix allows us to construct that matrices Mij. Then we need to compute the main characteristic polynomial of U1 and the companion matrix C of MU1. We already seen that W1 is 2, and we can then calculate compute the matrices U1 that depends, of course, of the universal adjacency matrix of G1. And after calculate, we have this result. We also compute using now this matrix the walk matrix WU1, and we have this matrix, and this implies that this is the matrix with entries 4 and 14. As I already said, this is used to the computation of the matrices Mij. Now, for the computation of the main characteristic, we saw that we can solve this linear system, and these are the coefficients of the main characteristic polynomial, that is this polynomial of order 2. And also with this vector, we can calculate or compute the companion matrix of MU1. The same is done for these computations involving this universal adjacency matrix of G2 and involving the universal adjacency matrix of G3. And with these three computations items, we can compute the H-join associated matrix W tilde with these entries, and then we have this matrix, and so the characteristic polynomial of this matrix W tilde is given by this polynomial of degree 5. With this, since we know the characteristic polynomial of each U1, U2, and U3, you have finally the polynomial, the characteristic polynomial of the universal adjacency matrix of the H-join of the family of arbitrary graphs. Okay, in terms of the this product and the characteristic polynomial of the matrix W tilde. And it's all. These are the references of our work. And thank you again. Thank you for your attention.
So
I hope I'm on schedule.
Yes, you are on schedule. So let me check if there are some questions here. So no open questions, but or comments. You can ask. I think you need. I don't know if you can hear or it has.
Yes,
you can hear.
Yes, yes.
There is a question here.
Hello, Sophia. This is
Hello. Hello, guys.
Nice to see you. Thanks for a nice talk. I just have one question. This example you gave, was that very specific? You had all these parameters equal to 1. So are there some general...
To be more easy, yes.
Easier. So in general, it's hard to compute, isn't it, for arbitrary parameters?
Sorry,
it's difficult to compute in general, isn't it?
Sorry?
It's hard to compute this explicitly in general. It only works for certain values of the parameters.
Of this gamma, delta.
Right?
No, I think well, I give this example with this to be easier to understand the example, but this is easy to compute for any values of this scalar because it's here. Okay.
Yes, let's see.
Because the construction of this matrix W tilde here is not difficult to calculate.
It means that it's 1 whenever there is.
I think you ask me if we change the parameters, the calculation, the computations are harder.
Yes, that's the question.
The hardness is here because, but I don't think the computation of the after we have this because in fact we have alpha and gamma here, and UI here, UI involves delta. Okay, delta, gamma, beta, and I think.
So this means you can find the H-join of any family.
The spectrum of
spectrum as soon as you know the individual spectra.
Yes, of the components of each component, G1, yes. G2, GP, and also we have to construct and. There is the construction, the computation of the H-join associated matrix. That is this one. Because the spectrum, the entire spectrum depends on the spectrum of each component, yes. And also depends on the spectrum of this W tilde.
Yes, that answers my question, because there is a hidden complexity in this last matrix. Yes.
This one, yes. The difficulties here is in terms of double tilt.
I see. Thank you. Thank you.
Okay. Thanks, Sophia, for the nice talk. So
And Raquel.
thanks for your participation. You need to stop sharing.
Yes. Okay.
And I think so. It's 3:20 in my watch. So the next speaker is Julia Lieb, and she's going to talk about construction of LDPC convolutional code. So it's a talk in coding theory. Yeah, yes.
So can you see the screen? Should be full screen now, right?
Yes, Julia, it's okay.
Yeah.
I don't know if you can hear me. Yeah, thanks.
So should I start or should I wait the 5 minutes?
No, in my watch I have 3:20, so I think we should start. So your talk was scheduled for 15:20, so
Okay, yeah.
we can start. Thanks.
Okay, yes, the topic of my talk, as said, is the construction of low-density parity check convolutional codes. And this talk is based on a recent paper, which is joint work with Gianniera Alfarano and Joachim Rosenthal. And we proposed in this paper to construct these codes with the help of a combinatorial object called difference triangle set. But before I explain this, I will give a short introduction on convolutional codes. So a convolutional code of rate k over n is defined as a free fz submodule of fz to the n of rank k. And yeah, this means that we can just view it as the image of some polynomial matrix G, which should have full column rank. And this matrix G is then called the generator matrix of the code. And it's unique up to right multiplication with a polynomial matrix U that is invertible over the ring of polynomial matrices. And for convolutional codes, we have a third parameter associated to the code, the so-called degree of the code. And it is defined as the maximal polynomial degree of the full size minus of G, and full size minus means here k times k minus. And we are interested in a special class of convolutional codes. Of course, if we want to construct low density parity check codes, meaning codes whose parity check matrix is sparse, then we need a parity check matrix. And not all convolutional codes admit such a parity check matrix, but we need a certain condition, namely we need that the generator matrix G, and if this is true for one of the generator matrix, then always for all, that they are basic, and this means they should have full rank for all Z from the closure of our field F. And we assume F always to be a finite field in this talk. And in this case, we have such a parity check matrix, and this allows us to write our code as the kernel of this matrix H. As always in coding theory, we also want to consider some distance measures because they give us the error correcting capabilities we want to have. And for convolutional codes, we have different notions of distance. First, the so-called free distance, which is the kind of usual distance because we just consider the minimum weight of all non-zero code words. And with the weight of a polynomial vector here, I mean just the sum of the weights of the coefficient vectors. And another distance we consider for convolutional codes are the chased column distances. And in this case, we consider this sum of the coefficient vectors only up to the chased coefficient. And in this case, we can rewrite this whole condition, replacing here the condition that V has to be a code word by the condition that this vector formed by the coefficient vectors V0 to Vj has to be in the kernel of this matrix Hj here, which is called the J sliding parity check matrix. And we obtain it by considering the polynomial parity check matrix, considering its matrix coefficients, and forming this sliding matrix in that way here. And I will also always assume here that H mu is unequal to 0, so mu should be really the degree of this parity check matrix. Now I want to come to the low density parity check convolutional codes. So the first thing we do now is to consider this MUST sliding parity check matrix. So the sliding parity check matrix where we really consider all coefficient matrices. And we view this matrix as the adjacency matrix of a bipartite graph, which is called the Tanner graph of the code. And then it is known that for the decoding of such codes, we want to avoid cycles in this Tanner graph because they are harmful in the decoding procedure. And especially they are harmful if it's a cycle of short length. And we can represent such a 2L cycle in the graph by an L times L submatrix of this MUST sliding parity check matrix, where this L times L matrix A has this form here, where the AI are just any non-zero values from our finite field. So originally, LTPC codes were considered over the binaries. And in this case, all the AI were just equal to 1. And then it's easy to see that the determinant of A is always 0. We now consider it for general finite fields. And in this case, it can happen that this determinant is non-zero. And in this case, the corresponding cycle is not harmful for the decoding. So what we want to do in our constructions, we want to construct such a MUST sliding parity check matrix, which then also defines the whole convolutional code in such a way that there are no cycles, or at least no small cycles contained, that don't fulfill this FRC full rank condition that the determinant of A is unequal to 0. So either we want to avoid this structure, or at least we want to have that the corresponding determinant is non-zero. And yeah, we want to construct this with the help of so-called difference triangle sets. So here I want to give the definition of these sets. So what we have is we have this script T is our difference triangle set. It's a set of sets, and each of the subsets is a set of integers that are in increasing order. And now we consider the positive differences between two elements of the same subset. So we form all the differences in between one of the subset of integers that are positive. And we get a weak difference triangle set if in between one of these subsets, all these differences are different. And to get a difference triangle set in the strong sense, we still consider only differences that are formed by elements from the same subset, but now all the differences we get in total have to be different. Then we have a difference triangle set in the strong sense. And there's one other parameter of this difference triangle set which will be important. It's the so-called scope of this difference triangle set, and it's just defined as the largest integer that appears in any of these sets here. I will give an example which also explains the name difference triangle set. So we have here a set consisting of two subsets of integers, and we want to form all the differences which are positive between the elements. So if we form just the differences between consecutive elements, so 2 minus 1 is 1 that appears here, 4 minus 2 is 2 that appears here, now 8 minus 4 is 4 that appears here. So this gives us the first line. And of course, now if we want to compute the difference between 4 and 1, it's the sum of these two previous differences. That's why in this second line, we have always the sum of the two entries above. And in the last line, we have then the sum of all the entries in the first line, because it's just the total thing. So h minus 1 is the sum of all the differences we had like in the first row. And we form, like for the second subset, we do it exactly the same. And now we see that we have here a weak difference triangle set, because in between one of these sets, we see that all the integers are different. And if we look at the total of the two triangles, then we see that the integers 2, 4, and 6, that they appear twice. So we only have a weak difference triangle set, but not a strong one. And next, I want to give an example. Sorry, somehow. Now it works again, sorry. Now we can see here a strong difference triangle set. And now we have here 3 subsets, and to each of them we associate this triangle as before. And now we can see that there's no integer through all the triangles that appears twice. So this is then a strong difference triangle set. So how can we now use these sets to construct our convolutional code? We need to define this coefficient h0 to h mu, and we can assume that h0 has full rank. Then we can do Gaussian elimination and bring this matrix to that form. So the whole code is defined if only this h bar given by h0 by a0 to a mu is fully defined. So we only need to define this matrix to get the whole code. And this is now done with the difference triangle set in that way that we have here k columns, and we take k triangles in our set, and to each of the columns we associate one of the triangles, and the integers in one triangle give the positions of the non-zero entries in the corresponding column. So with the difference triangle set, we can only define which entries in this matrix H bar are 0 and which are non-zero. So we do not specify the values of the non-zero entries, that we will only do later. But we will see now in the following that some properties can already be shown just with the structure of which entries are 0 and which are non-zero. And of course, this only defines then our h bar and not how we split this into this h0 to h mu. Since they have all the same number of rows, basically we only have to say what mu is. And we calculate this mu with this formula here, where the scope of the triangle comes in and the pre-described rate that we want to have. And basically we do it in that way that we avoid to have any 0 rows at the end of h bar. Yeah, and as I said, there are some properties that we can already show without specifying the values of the non-zero entries, just with the structure given from the difference triangle set. And one of these things is the distance. So if we have a KW difference triangle set, means that each triangle has W elements. And this means that each column of our h bar has weight W, and with this we can compute the free distance. And if we cut here after the aj, this matrix h bar, and define the minimum column weight of this matrix as wj, this allows us to compute the j's column distance. And one other thing is we can also, with properties on the difference triangle set, ensure that our corresponding graph will contain no cycles at all. And this means if it contains no cycles at all, that the rank and the non-zero entries play no role. So this also works then, over every base field. And the conditions we need to impose on our difference triangle set is that all the first elements in one of the subsets are equal to 1. And none of the differences that occurs anywhere is divided by n minus k. And now I want to specify the values for the non-zero entries to be able to relax these conditions on the difference triangle set a bit. So we just take the IL entry of the H bar as alpha to the I times L, where this alpha is a primitive element of our finite field of Q. So this looks then like this in an example. So the first triangle gives us the support of the first column. So in row 1, 2, and 6, we have something non-zero. Then the same for the second column. In position 1, 2, and 4, we have something non-zero. And with the specified construction now, in the first column, every element is an exponent of alpha, where the number of the row gives the exponent. So in the 6th row, we have alpha to the 6th. And in the second column, just everything is an exponent of alpha square. And again, gives the position of the row, gives us the exponent. So in the 4th row, we have now alpha squared to the 4 is alpha to the 8. And with the formula I showed before, we can also compute the distances here in this case. So for the zeros column distance, we have to cut here after the first row and say what is the minimum column weight, which is here obviously 1. And then we have this distance is 1 plus 1 equal to 2. And then for the distances 1 to 4, we have to cut after the second, third, fourth, and fifth row. And then always the minimum column weight is 2. So the corresponding distance is 3. And then at the end, if we have the whole thing, the minimum column weight is 3. And therefore the free distance is equal to 4. And now what about the cycles? We want also to ensure that we have no short cycles whose determinant is 0 in this Tanner graph. And therefore we have to distinguish if we have a 2L cycle where L is odd or where L is even. So this theorem gives us the situation if L is odd. And in this case, it is enough if we just have a weak difference triangle set. We do not need any other condition on our set. And the field size has to be larger than this expression here. And this is like essentially linear in all the parameters, which is quite nice. The problem here is the case when L is even, that it gets much more complicated. So complicated that I did not even write it down because it's not doable in this rather short talk. The problem is not the field size that stays in the same order. The problem is that we get some complicated condition on our difference triangle set in the case that L is even. And this is then why we modified our construction and use here a P to the I instead of the I. And this has the effect then that we need a easier condition on the difference triangle set compared to the complex one that I didn't show. Namely, we need just the difference triangle set in the strong sense, and that the first values of all the sets are equal to 1. This is enough. But then our field size gets larger than shown in the previous theorem, because our prime P has to be larger than L times K, and the field size then larger than this expression to exclude these 2L cycles that don't have full rank. So we could relax then the condition on the difference triangle, but we get now a field size that is exponential in the parameters. So in summary, one has to decide if one rather wants to have a larger field size and easier conditions on the triangles or the other way around. Yeah, and this brings me to the end of my talk. Thank you very much for the attention, and also thank you very much again for inviting me.
Thank you, Julia. You need maybe to stop the sharing of the screen. We'll check questions and answers. So no open questions.
I have a question. Can I?
Raquel, yeah.
Yes, just a quick question. Julia, in what these are convolutional codes, but they are somehow different from the classical ones. What are the advantages considering these codes when you consider the others? Let me say, the decoding is, I know that the LDPC codes, the block codes, the decoding is faster. What here in this case is the same, but do you have MDS convolutional codes or MTP convolutional codes? What are the similarities or the advantages and disadvantages considering the other codes? Because I really don't know anything about LDPC convolutional codes.
Yeah, I mean, we saw that like this free distance depends on this W, which was the column weight of this H bar. So that means if it is sparse, then we can't have like something like MDS, because the sparser it is, the like smaller the distance is. So we kind of have to find a trade-off between like large distance or faster decoding.
Mm-hmm.
So yeah, it's like if we have these decoding algorithms that we have for LTPC convolutional codes, we can't have something like MDS or MDP. This is because of this sparsity of the parity check matrix that is then hard to get. But in turn, we can use this like good decoding algorithms for LTPC block codes also for these codes.
Okay, thanks.
Thanks, Julia, for the nice talk. And we have 1 minute, no, 3:40 here. So the next speaker is Veronica. We were here with some technical problems, but it's...
Sorry. Thank you. Hi, everyone. So I can share my screen.
Yeah. Veronica is going to talk about block top list matrices for burst correcting convolutional codes. So Veronica is from the University of Alicante.
Thank you very much. And thank you, the organizers, to invite me to this great conference. So thank you. I would like to introduce this talk talking about the other authors, Clement and Nav, who are work with me. Some motivation to introduce the construction of this convolutional code is in the communication process, the transmission of information brings implicit the use of communication channels. So these channels are imperfect and suffer the effect of noise and perturbations, which can affect the messages sent. So the source can arrive altered to the receiver, and we need to recover the information sent. So a solution for this is coding theory, because the error detecting and correcting codes add a redundancy to the information in order to achieve reliable communication. So in this technological world, we use constantly multimedia applications such as video conferencing like now, or mobile gaming, cloud computing, and sometimes these applications can suffer from congestion as routers fail, so and produce the loss of cluster of packets. So the streaming applications and the streaming communication require that the data is transmitted sequentially in real time under strict delay. So long delays are usually unacceptable. We need to recover instantly the information. So classical error correction codes are far from the ideal streaming codes, and we usually use convolutional codes. So Julia has introduced a lot of about my preliminaries, so really good. No, you know more than convolutional codes now. So the first authors who introduced this kind of convolutional codes to construct in streaming, this called streaming codes, were Martinian, with a construction establishing a relation between the decoding delay, the burst iteration length, and the rate. And Kisti and other authors presented other burst erasure correction code, which correct burst erasures and isolated erasures, how we study in this talk. So now we present a simple class of encoders which admit the shortest possible decoding delay to correct burst of erasures of a given length, and is really easy to implement. So in our construction, we use a block toplets matrix, are a matrix composed by other matrices, and we will use upper triangular matrices. So something about block codes and convolutional codes, the best and the worst, not to use in inverse channels. So a block code is it can be defined as a k-dimensional linear subspace of Fn, and the information is divided in blocks and encode them with the same procedure and independently. So any block you encode, the next you encode, they don't have any relation between blocks. And the messages are encoded, adding redundancy information. So they have good error correcting properties, and algebraic decoding algorithms are easy to implement. But for these streaming applications are not good. So we need the convolutional codes, because the information is considered as a whole sequence divided into blocks of a fixed length and taking into account its position. So we need the position because we are going to have a relation between the different blocks. So these blocks are not encoded independently. These kind of constructions using convolutional codes are suitable to streaming applications. Only to look a little bit the difference between to encode with a block code or a convolutional code is the following. We can assume that the information is a matrix, or this matrix can consider as a vector where the elements are other vectors as the colors. So if I have this vector of information, I encode with the block code only using the generator matrix, and we do the product U0 by J, and I have in the time 0 this the information encoded, B0, and B1 is U1G, and so on. But to introduce the convolutional code, we can introduce the delay operator D for block code 2. DS only indicates the time instant in which its code word was transmitted. So U0 is in time 0, U1 is in time 1, and U2 is in time 2. So this is the same, only adding the delay operator. But when we have a convolutional code, we use a generator matrix with a memory. So it's like a polynomial of matrices depending on the delay operator. So when I have to encode vector information, U0 by GD, all these parties, all this information vector by GD, we can observe the following. U0 only appears with G0, but B1 it depends on U1 and U0. So in the time 2, V2 depends on not only U2, for U1 and U0 too. So all the packets in the time t depends from its previous information. So for block codes, we have only any information vector by G, but for convolutional codes, any information vector depends on the previous information. We can say that a block code is a convolutional code without memory. This is a formal definition introduced by Julia, and I would like to remark the sliding matrix is an per triangular matrix, and with this block doublets matrix. So we are going to use this sliding matrix to decode, to recover the information lost, not to decode. So we work in vast erasure channels. These kind of channels, when we encode the information using the convolutional code, we have the information encoded, and we need we can obtain this packet VI, the code word, either arrives correctly or is completely lost. So we can have different packets lost, and after we receive a correct information, and other lost or other burst can occur, okay? So we define L is the maximum length of the burst. Imagine that I have 2 packets lost, but after I have 3 packets lost, so I decide that L is 3. And T is called the decoding delay. this is all the packets that I need, the source packet that I need to receive to recover the lost packet. So our main goal is to build encoders that allow to recover burst as soon as possible. So Martinian introduced this relation between the decoding delay, the length of the burst, and the rate of our code, our convolutional code. It has to be satisfied to be a good correction, to correct all the burst. So why we use convolutional codes? We have some advantages and disadvantages. So the convolutional codes are good because they have a convolutional code with large column distance, are very appealing for sequential decoding and have excellent error correction capabilities. But they require large finite fields and long delays, and they don't generally achieve the best trade-off between all these relations: delay, redundancy, field size, and burst correction. So we try to construct a simple system encoder to this kind of burst channel. So we are going to define the generator matrix that we use to encode an information vector. So this generator matrix is in a systematic form. It means that I have the identity matrix at the beginning and other matrix GD. And the first part allows us to recover the source packet. So we don't need to decode after. Directly we have. If I multiply my information vector with this GD, define it as a block doublets matrix or this sliding matrix, we obtain the following information. The first part is composed, the first vector V0 is composed by the source packet, so we don't need to decode. And after, the second part is the encode information. So in the following, we obtain the same, but if we observe, we have dependencies between the source sent and the rest of the packets sent before. So we are going only to observe the part, the second part, the encoded, and we are going to try to use this for to obtain the recovery information that we have lost. So some premises, we have L is the burst, the length of the burst, and we firstly do the case when K is greater than A minus K, so we can express K as this sum. And we are going to take into account when gamma is different from 0 or 0. And remember that our generator matrix is in this way, in a systematic form. So this matrix is built in the following way. We are going to construct matrices composed by zeros and identities only, in this case, when we have a multiple of L. In the rest of the cases, we have 0, and in the case when gamma is different from 0, we need to add other matrix in this way. So to recover the lost information, we need this matrix. And with this matrix, we are going to do an example. Okay, so the idea is to recover all the information. We need only to solve a linear system with this matrix. These are the packets lost, and B is completely known. So if we imagine that we have received a burst of erasures, we have this, the L is 3, so we have lost the packets V0, V1, and V2. And by the Martinian relation, we need that T is greater than 6. So we are going to do this with the parameter T equals 6. We need to have 6 packets. We need to receive 6 packets correctly to recover this burst. So we use a convolutional code with the parameters k and n 4 and 6 respectively, and we have that in this case gamma is different from 0. So at instant t0, I receive v0, instant 1 v1, v2, and these are lost. So at the instant t6 here, when I have v6, I'm going to recover u0. At instant t7, I'm going to recover u1, and the instant t8, I'm going to recover u2 in the following way. To recover u0, I have to solve the linear system x0, x1, x2 with the truncated method defined before, and these terms are known. I'm going to explain v0, v1, v2, and v3 in the following way. So if you look to recover x0, because in this step I'm going to recover x0, I only need to know v3, v4, v5, and v6. In the following way, these are examples to this case to know how I can construct the truncated matrix. If you look, are all matrices with identity and zeros, zeros and identities. And in the first linear system, we obtain the parameters of U0. In this case, the four elements of U0. To obtain U1, we do the same, but now I have to solve the system with the variables x1, x2, because x0 I have, and u3 I know. So this system is reduced, is simplified. So it's easier to do than the first. So to recover u2, I do the same, this linear system, but I have only an unknown x1, but the rest are known. So this system is reduced and is easier to do. So at the end, we don't need to decode our process using the systematic form. We have directly, when I receive the encoded information, I receive the source packet, and after to recover, I only need to solve a linear system. So the proposed construction admits an optimal delay decoding. The t is the less than we need, only for burst of erasures of length up to L. And this construction requires only binary entries, whereas previous contributions require larger finite fields, and then the decoding is computationally more efficient. The other case, when k is less or equal than n minus k, we only need to define this matrix, and it's easy to solve it. Some open problems, okay, or some disadvantages of this construction. The problem comes when L is 1, because our method is not optimal, because these values k and n are close, since that value of t increase fastly. Other future works that we would like to solve. When we assume that from a burst to other burst, all the information that we receive are correctly, but we would like to know if we have an isolated erasure, how we can do this. Some ways that we are researching are: try to recover the isolated erasure using MDP codes, and after, in a second step, try to recover these burst erasures with our method, because we know that for isolated are not good. It's not good, this construction. And try to do a concatenation of two convolutional codes, one with MDP code and other with this construction, and try to do in two steps, try to solve the burst and the isolated erasures. So thank you very much for your attention, and I open from your questions.
Thank you, Veronica. Now you need to leave the screen, maybe?
Yes.
So let me check if there is any question here. What happened here? no questions, but
I have one question, if I may.
From
Yes.
the theory, so
Yes. So Veronica, your codes, they are very suitable for dealing with bursts, and they are, let's say, better than the MTP because they are computationally more efficient, because they don't have large fields, because it's it's the only thing, although it's a huge thing, but because the MDP convolutional codes can also correct this type of bursts, can't they?
But for example, in this case, we do the decoding directly. Using this systematic form, we can use it. We don't need to decode anything. We obtain directly the decoding, and we can use this part to try to recover the rest of the burst.
You say that okay. You say that you don't need because the U is inside the
yes, it's inside so of your yes. Of your, when you receive the information encoded, so you have directly, if it's correct, if you receive correctly, you don't need to decode. But if not, you need to use this linear system to try to recover the information, and you can use in the rest of the terms that you know to try to know it.
Okay. Okay,
and we work with binary, so it's really fast. You don't need to work with finite fields, large finite fields. But we haven't compared with other constructions, so we need to do more. This is a preliminary result, so we need to study more. We don't know about the distance. We know that it's not really good, so this is a bad,
yeah. So maybe the distance is not good, but if it's efficient decoding, so it's enough. But maybe you need a large degree of decode, a lot of matrices, in order to be able to correct a lot of bursts. Okay. Thanks.
Thank you, Veronica.
Thank you very much.
And our next speaker is the main speaker of the session, and it's talking graph spectra. Is Lorenzo Sciardo. Lorenzo, are you there? He's starting to sharing the screen. So Lorenzo is going to talk about Caminess constant and the twin paradox for graphs. So he's at the moment at the University of Oxford.
Hello. Thank you very much, Anida, and thanks a lot for the invitation, Anida and Raquel. So I will talk about Caminess constant and the twin paradox for graph. I will start with some preliminaries, which basically will consist in defining Caminess constant. The first part of the talk will be about bounding Caminess constant for trees. And then after a short interlude, I will talk about a paradox involving Caminess constant and three road extensions of road networks. So let's start with Markov chains. So we consider a discrete time finite state Markov chain, which is a stochastic process that we should think of as a system that at any time can occupy one of a finite number of states and can transition between states in discrete time steps, following some fixed transition probabilities, call them Tij. And the key point is that these probabilities do not depend on the previous history or the previous trajectory. So this is the Markov property. Of course, we can take all these transition probabilities and encode them in a matrix, the transition matrix. So we observe that this matrix here is, well, entry-wise non-negative. This is because probabilities are non-negative numbers. If we are on a vertex I, on a state I, then of course we have probability 1 of going to some other state in the next time step. So this means that the row sums of this matrix T are all ones, or we can write this as T times the all ones vector equals the all ones vector, which means that 1 is the dominant eigenvalue of T, corresponding to the right eigenvector all ones, applying the Perron-Frobenius theory. Also notice that T completely determines the stochastic process once the initial probability distribution P is known. This is because for any number G, P transpose T power G gives the probability distribution after G steps. So this means that we can just study the entire behavior of the chain just by looking at matrix theoretic properties of T. We will suppose that T is irreducible. So this means, well, on a probabilistic point of view, this means that given any pair of states, I and J, I can always arrive to J after a finite number of steps with finite probability, starting from I. From a graph theoretic point of view, this means that the directed graph associated with the chain is strongly connected. And on a matrix theoretic point of view, this means that T is not permutation similar to a block upper triangular matrix with non-trivial blocks. Also, we may assume that, well, another property that T may have, but we're not going to assume it, is that T power G is entry-wise positive for some G. Right? So if this is true, then T is said to be primitive. Okay, so what is Kemany's constant? Well, so we saw that T has a right Perron vector, which is the all ones vector, relative to the eigenvalue 1, which is a spectral radius. We may look at the left Perron vector of T, call it W, and suppose that W is normalized in a way that the sum of the entries is 1. So if we look at the conditions that we have now, then, well, first W transpose T is equal to W transpose. This is because W is the left Perron vector. W is entry-wise positive. This comes from the Perron-Frobenius theory. And, well, W transpose identity, W transpose all ones vector is equal to 1 because we are choosing it to be normalized. So looking at it from a probabilistic point of view, then this means that W is a stationary probability distribution of the chain. So it's fixed under an application of the chain. If you're given any initial probability distribution P, then we have that, well, this equation holds. So this means that for any state I, Wi is the long-term average time that the process will be in state I. And this can be made a bit stronger if we assume T to be primitive. In this case, given any initial probability distribution P, the process will always converge to W. So the limit of P transpose T power G is equal to W transpose. So this, in a way, means that W encodes the long-term behavior of the chain. It tells us what will happen in the long run. We may also ask ourselves what happens in the short term. So what happens in the next few time steps. And this is encoded by the mean first passage matrix, which is a matrix M, whose ijth element is the expected value of the number of steps I need, starting from I, to reach J for the first time. So you see that this only cares about the next few time steps. This matrix here, as many other quantities of Markov chains, has a recursive expression, which is this one. And using this, it can be shown, as Kemeny and Snell did, that if we take the short-term object, so M, and we multiply it times the long-term object, which is W, what we obtain is a constant vector. This is quite surprising, and a common entry of this vector here, diminished by 1 for some technical reasons, takes the name of Kemeny's constant, and it's the main object in this talk. We denote it as kappa of T. Just notice that kappa of T is a spectral quantity of the matrix T. This is because it was shown by Leven and Loiseau that if tau 1 up to tau n are the eigenvalues of T, then we have this expression for Kemeny's constant in terms of the spectrum. So it's the sum of 1 divided by 1 minus tau I, where tau I are all the eigenvalues different from 1. So we have this spectral quantity, this spectral expression. We will see that there is also a combinatorial expression later in the talk. Okay, so now I want to restrict the attention a bit, and I want to talk about random walks. So the idea is that we start with a connected, undirected graph G, and we consider a kind of natural Markov chain on G. So the state set is going to be the vertex set of G. I want that whenever I am on a state I, or vertex I I can go in the next time step to each of the neighbors of I, and all of them can be chosen with equal probability. So this amounts to saying that T has to be the adjacency matrix A, but of course rescaled in a way that it is a row stochastic matrix. So we have to pre-multiply it times the inverse of the diagonal degree matrix. Okay, so this gives us a Markov chain. Here you see an example. Of course, we can also decide to start with a probability distribution and see what happens. So here the shade of green means the weight assigned by the probability distribution to the state. And we see that after just a few steps, we will converge on a fixed distribution. And this is because this graph here happens to correspond to a primitive random walk, which is basically the same as saying that there exists some directed cycles in the graph having co-prime length. Anyway, so we are given a graph G. We associate with it the random walk, and then we can talk about Kameny's constant of G as Kameny's constant of the random walk, right? So kappa of G is well defined. From the definition of Kameny's constant, we can rewrite it in the following way. So it's the sum taking over all I and j's of wi, wj, mij. Again, -1 for some non-important technical reason. And looking at this expression, we can see that Kameny's constant actually measures the number of steps I need to go from I to j when I and j are both sampled at random, but not uniformly, instead according to the long-term stationary probability distribution, right? So this means that in a way, Kameny's constant is a measure of the long-run ability of the graph to transmit information from one vertex to another. If Kameny's constant is very high, then it will be difficult to travel in the graph in the long run. But if it is small, then I would just need a small amount of steps to travel in the graph. So it's a kind of connectivity notion, connectedness notion of the graph. Okay, so now I will talk about bounding this parameter for trees. This is part of a joint work with Geir Dahl from the University of Oslo and Steve Kirkland from the University of Manitoba. So intuitively, if we have a tree which is big, so it has high order and high diameter, then, well, it should be more difficult to travel in it. Right? Now we want to make this more explicit. We have to define a notion which is reminiscent somehow of a physical notion, which is the moment of a rooted tree. So consider a rooted tree, a tree having a distinguished vertex. And let's draw it on a plane, starting with the root, which is considered to be fixed in a way, so a fixed fulcrum of this object. And then we draw the rest and we try to arrange the vertices horizontally. And also, we let the degree of a vertex to be its weight, or equivalently its mass, right? Then we can imagine that the gravity force is acting on this tree. And whenever we have a set of forces, we can consider the moment or the torque of the set of forces. Each one of these forces has to be applied to some specific point particle. And the moment is the sum taking over all the points of the vector position, vector product, the vector force. So this is the physical notion of moment, and then we can transfer it to our setting. So we can consider the moment of the gravity force acting on the tree, and mu of r is going to be the magnitude of this moment, right? So its expression is the sum taking over all the vertices of the distance of the vertex from the root times the degree of the vertex. Okay, so we now want to take a generic tree and try to decouple Kameny's constant into Kameny's constant of its parts. So here's the construction. We have some rooted trees, R1 up to R4 in this case. The concatenation of them is this unrooted tree here, which is obtained just by connecting the roots in sequence of the single rooted trees. We can then express Kameny's constant of T, of the concatenation, as a combination of Kameny's constant of the parts, plus some other things. So it's not really important what appears in this formula. There are some constants which are, for example, n, number of vertices, k, the number of parts. Then there is m, which is a vector of the sizes of the rooted trees. X is a fixed Toeplitz matrix, like the one in the talk by Veronica. And then what I want to focus on is the vector mu, which contains the moments of the rooted trees in the concatenation. So in a way, a bit intuitively, we can say that Kemeny constant of a composite tree is kind of additive, so only depends on Kemeny constants of its parts, some constants, and then the moments. So in a way, the moments measure the non-additive behavior of Kemeny constant with respect to composition or concatenation. It's even more clear if we consider the following construction. So let's say we have a tree T and we have a pendant vertex of the tree. Then we can view T as a concatenation of a trivial rooted tree, only consisting of V, and then T minus V. So the concatenation of these two trees. And then if we apply the concatenation formula, we obtain this expression here, from which it's clear that Kemeny is a combination of T minus V, of Kemeny constant of T minus V, and the moment of T minus V. So also in this case, we see that the moment appears in the formula. Okay, now we want to use this to get a lower bound on Kemeny constant for trees. So we start with a generic tree and we identify a path in it, which is in red here. We can turn T into a caterpillar tree by taking each vertex which is not on the path and making it adjacent to the closest vertex in the path, as you see in this example here. So if we do it for all the vertices in the tree, then we obtain a tree such that all the vertices which are not in the red path are adjacent to some vertex in the path, which is exactly a caterpillar. And the key point is that this operation decreases Kemeny constant. So intuitively, it's easier to travel in this tree here than it is to travel in this tree here. We will see later that our intuition on Kemeny constant sometimes it can be wrong, but here it's right. So it's easier to travel here. But then, well, we can also see a caterpillar as a concatenation of rooted stars. This means that we can apply the concatenation formula I showed before to get an analytic expression for Kemeny constant of a caterpillar, and then we can minimize it analytically over all caterpillars having a fixed order and a fixed central path length. And we obtain that this caterpillar here is the minimizer of Kemeny constant. Of course, some care has to be taken when the length of the central path is odd or even. So there are two different cases, but this is basically what happens. And if we combine these 2 points, then of course we get that a lower bound for Kemeny constant of a tree is given by Kemeny constant of this caterpillar here. And from this we have an asymptotically sharp lower bound on Kemeny constant for trees having fixed order n and fixed diameter delta, which is here. So Kemeny constant is more than n plus 1/3 diameter square minus the diameter minus 1. Okay, let's try now to do something similar for an upper bound. Well, here we can actually apply directly the concatenation formula, but in a recursive manner. And we can use the seesaw principle, so-called. So if we want to maximize the moment of an object, intuitively we have to push all the weight as far from the root as far from the fulcrum as possible. So here the same happens. And using this, we get that Kemeny constant of T is less than number of vertices times the diameter minus 1/2 of the square of the diameter. Is this asymptotically sharp? Well, yes, it is. And now I will also say what I mean with asymptotically sharp. So there exists a sequence of trees whose orders go to infinity, such that the limit of Kemeny constant of the tree divided by the upper bound is equal to 1. So in the long run, Kemeny constant will coincide with the upper bound. And the tree is used to witness this theorem are broom stars, which are, well, these trees here, obtained by taking some rooted stars and identifying their roots. It's not very easy to compute Kameny's constant of broom stars using the definition. But it turns out that we can actually avoid this problem. So we can just view broom stars as a concatenation of a smaller broom star having one less arm, a star, and then some trivial trees having only one vertex. And then we can basically apply the concatenation formula before to obtain a recursive relation which has to be satisfied by Kameny's constant of broom stars. And now all we have to do is to guess one expression, which we can do, for example, on MATLAB by using regression on a large sample of broom stars, and then check that this expression here satisfies the recursive relation. So this is actually how we computed the expression in the paper. Okay, so now before going on with the second part of the talk, I want to, there will be a small interlude, which will just take 2 moments. So the idea here is that we saw that Kameny's constant is a measure somehow of connectivity. There's a much more famous notion of connectivity, spectral notion of connectivity for graphs, which is the algebraic connectivity. So the second smallest eigenvalue of the Laplacian matrix of the graph, introduced by Fiedler. Interestingly, for trees, but actually this can be extended for general graphs, but now I just want to focus on trees. Both these notions here of connectivity are somehow related to certain moment notions for rooted subtrees of T. Why is that? Well, for Kameny's constant, we already saw it. So Kameny's constant is almost additive with respect to concatenations, but it's not completely additive. And the moment is exactly what encodes the non-additive behavior in a way. For the algebraic connectivity, the situation is a bit different. Here I will be very imprecise because I don't want to introduce many new objects, but I just want to say that the algebraic connectivity can be obtained by balancing the Perron value ρ of bottleneck matrices of rooted subtrees of T. So what does this mean? Well, whenever we have a rooted tree, we can consider its bottleneck matrix, which is the symmetric matrix M, whose ijth entry is the number of vertices simultaneously lying on the path joining Vi to the root R and in a path joining Vj to the root R. So we get this bottleneck matrix, and then this is a positive matrix, so we can apply Perron-Frobenius theory. And we can consider, in particular, its Perron value ρ. So it turns out that if we find somehow a place in the tree, a vertex or a pair of adjacent vertices, which best balance the Perron value of bottleneck matrices of rooted subtrees at this point, then the algebraic connectivity is the inverse of the Perron value. So we can recover it from this Perron value of rooted subtrees of the tree. And well, it's natural at this point to consider ρ as the spectral analog of mu, so some kind of spectral moment of the rooted tree. And so it's natural also to ask the question, how do these two moments compare, since they are both connected to some connectivity notion? Well, first, the moment is almost an upper bound for ρ, for the Perron value. So the moment is always more than ρ of R minus 2. The ratio mu divided by ρ is at most linear in the number of vertices, so it's at most 4 divided by 7 times the order. But it feels like we can actually do much better. So for example, if we look at stars, then the limit of the ratio, as the number of vertices in the star gets bigger, is equal to 1. So in the long run, these parameters are kind of the same. For rooted paths, then the limit of the ratio is again bounded, is again a finite number. So it's pi squared divided by 4. And since, well, stars and paths are somehow the two extremal classes of trees, we may think or conjecture that actually the ratio is always bounded. This is not quite true. So for any alpha, there is some rooted tree R such that the ratio is more than alpha. But the so the examples for this have to be taken in a set of somehow fractal trees. So here we see two examples. One is the rooted Bethe tree. So it's this tree here, which is defined recursively. So here is a Bethe tree having 3 levels, 1, 2, and 3, and then 4 vertices attached to any vertex at each level. And if we make the number of levels go to infinity, then mu divided by rho is not bounded and actually behaves like the logarithm of the order. Another example of this fractal construction. So the rooted power of a fixed rooted tree R. So we start with R, a rooted tree. Here the square is always the root, by the way. R power 2 is this tree here. So it's obtained by R, identifying every vertex in R with the root of a copy of R. And then we go on. So R power 3 is obtained by R power 2 by taking each vertex of R power 2 and identifying it with the root of another copy of R, and so on. So we obtain this class of fractal trees. And as the power goes to infinity, also in this case, mu divided by rho is not bounded. And also in this case, its behavior, it behaves like the logarithm of the order. So of course, a natural conjecture at this point is that there exists some alpha 0 such that mu divided by rho is less than alpha 0 times the logarithm of n for any rooted tree. So the ratio is not bounded above, but it's at most logarithmic. This is just a conjecture, it's not proved yet. Okay, so we can now go on with the second part, so a paradox involving Kemenis constant. So, well, in this paradox, we will consider graphs to be road networks in a way, and we will ask ourselves what happens if we decide to build a new road. So we saw that, well, Kemenis constant is a connectivity notion. And we saw that if we measure the connectivity through the algebraic connectivity, whenever we add a new edge, then the graph gets more connected. This is a result due to Fiedler. We may then ask whether the same thing also happens for Kemenis constant. So we have here a graph. We decide to add this extra edge. If we consider vertices of the graph as cities and edges as roads connecting to cities, then we decide to build a new road. And then in this example, we see that Kemenis constant drops. And this is not really surprising, right? Because, for example, if you want to travel from this city here to this other city here, then before we needed to take at least 2 roads, so 2 time steps. But now there is a fast road, which if we are lucky, we can take, and then we can go from here to here in just 1 time step. So it's not a surprise that the communication will be better. So more roads imply easier communication. In 1969, in Stuttgart, Germany, they invested some money into the construction of a road network. But the traffic situation did not improve until a section of the newly built road was closed for traffic again. And then the traffic improved again. In 1990, in New York City, they had to close 42nd Street for a celebration, which is usually a very congested street. And the traffic situation actually improved then when they had to close the street. And there are many other examples of this kind of paradoxical behavior. And it turns out that they are all instances of a phenomenon which was actually studied mathematically by Bryce. So he wrote that there is the possibility that extending a road network by an additional road causes a redistribution of the flow in such a way that increased travel time is the result. So we add an edge, we add a road, and the result is that the communication is worse. Of course, this result is in a kind of different setting. So Bryce assumed that the drivers are somehow clever, so they would try to minimize their travel time. And so there is some game theory involved in his result. But it turns out that even in our simplified setting in which drivers are like random, the paradox can still happen. So here you see an example of a road network or a graph, such that if we add this road here, then the communication becomes worse. So traveling in this graph here is significantly more difficult than traveling in this graph here. Okay, so now the problem is to understand whether this paradox happens often and try to study when and how and why it happens. So we define a graph G to be paradoxical if there is some non-edge E, such that adding E to G makes Kameny's constant increase. So exactly as in the example. Also a little different notation. So now G is a graph, V is a vertex. GV with two edges is exactly what you imagine. So the graph obtained by taking two additional vertices and making them adjacent to V. So these are called pendant twin vertices. GV with a triangle on the top is obtained from GV with two edges, just by adding the extra edge joining the two additional vertices, as you see in this picture. So we say that G is V twin bias if Kameny's constant of this third graph here is bigger than Kameny's constant of the second graph here, which in a way means that this graph here is paradoxical. Also, we say that G is twin bias if it is V twin bias for every vertex V, right? So if this behavior happens for every vertex V. Okay, so why do I care about this, this construction here? The reason is that it was shown by Kirkland and Zhang that if we have a non-trivial tree, then it is always twin bias, right? So if G is a tree, then this construction always leads to the paradox. And using this, they also prove that almost all trees are paradoxical. So if we consider random trees having increasing number of vertices, then with a probability approaching 1, we will pick a paradoxical tree. So in a way, the paradox is actually quite frequent, at least in trees. What I want to do now is to show that actually this can be extended a bit. So every non-trivial connected graph is twin bias. And almost all connected planar graphs are paradoxical. So to do this, we start with finding a more convenient expression for Kameny's constant. So we saw in the very beginning that Kameny's constant has an expression in terms of the mean first passage matrix. This is the kind of the most intuitive expression, but also the least operative because it relies on the mean first passage matrix, which has only a recursive definition. Another expression is the spectral one in terms of the spectrum of the transition matrix. Here I will show that there is a third expression found by Kirkland and Zhang, which is totally combinatorial and is in terms of this two-forest matrix of the graph. So given a graph G, its two-forest matrix is the n by n matrix whose ijth entry is the number of spanning forests consisting of exactly two trees, TA and TB, such that Vi is a vertex of TA and Vj is a vertex of TB. So here's an example. This is a graph. These are two vertices Vi and Vj. We can, for example, consider this forest here, where this is one tree and this is another tree you don't see because it's the trivial one, consisting only of the vertex Vj. So this would be a proper forest appearing in the definition. This is another example. This is an example where all both the trees are non-trivial and so on. So we get in the end 8 possibilities, which means that Sij is equal to 8. And then of course you have to complete our matrix with other pairs of I and j. Okay, so using this, Kirkland and Zhang show that Kameny's constant of a graph is equal to the Rayleigh quotient of S of this two-forest matrix and the degree vector normalized times 4 times the number of edges times the number of spanning trees. So we have this beautiful combinatorial expression for K-means constant, which is much easier to work with respect to the probabilistic and the spectral one. Okay, so using exactly these objects, we can also define, given a vertex Vi, the quantity beta I of G, as you see here. So it's not really important how it is defined, but the thing is that this gives us a combinatorial test to check whether G is Bi twin Rise. So if beta I of G is non-negative, then G is Bi twin Rise. Actually, in the paper from which this is taken, there is an if and only if condition, but it's in terms of a more complicated quantity than beta I of G. But for this talk, we just need one direction, so it's enough to consider this object here. And of course, now we have to understand when and why this quantity is non-negative, because we see that this is a difference between two negative things. One way to understand it is to look at the resistance distance of a graph. So we consider a graph G, and we try to turn it into an electric circuit. How do we do? Well, we put a resistor of resistance 1 ohm on each edge. It could be a light bulb or a heater. And then, of course, you have to give some power. So we take a battery and we choose two vertices and we connect the vertices through the battery, as you see here. So now it's a proper electric circuit, and the heaters or the light bulbs are on, and there is some resistance in this circuit. So what is the value of the effective resistance omega ij? To find it, we can, for example, use the Ohm-Kirchhoff's laws, which say that whenever we have some resistors in series, then the total resistance is additive, so it's the sum of the resistances. Whenever the resistors are in parallel, the inverse of the total resistance is the sum of the inverses of the resistances. And notice from here that, in particular, the total resistance in this situation is smaller than any individual resistance. Okay, and then, well, combining and applying repeatedly these rules, we are able in the end to find omega ij. But it turns out there's a much neater way, which is using this theorem due to Klein and Randich. So if L is the Laplacian matrix of G and L dagger is its Moore-Penrose pseudo-inverse, so L is not invertible, but then we have to consider its Moore-Penrose pseudo-inverse. Then the resistance distance matrix omega, which is obtained by stacking together all the omega ij's, have this simple expression. So it's a diagonal part of L dagger times the all ones matrix J plus J times L dagger diagonal minus 2 L dagger. So this expression in terms of the pseudo-inverse of the Laplacian. Let me just say that as many other results on the resistance distance matrix, this result appeared in a journal on mathematical chemistry, and this is not a coincidence. And the reason is that in the chemistry community, this resistance distance is quite popular. And the reason is that they often have to find a way to measure the distance of elements in chemical compounds. And of course, one can represent the chemical compound as a graph. And so the most intuitive way to represent the distance is just to consider the normal graphical distance, so the length of a shortest path. But this is not really what they want, because whenever we have, well, the normal distance in a graph says that if we have many connections, so many shortest paths connecting the same pair of vertices, then their distance is the same. So it doesn't depend on the number of connections. On the other hand, well, if we are in a chemical compound, we want that if two elements have a lot of bonds, so have a lot of connections, then we would like the resistance to be smaller. And the resistance distance captures this phenomenon, and this is due to the second Ohm-Kirchhoff's law, right? Because here we see that if we have many possible connections in the graph, then the distance somehow gets smaller. So this is exactly the distance chemists need. And why do we need? Well, the reason is that this matrix omega happens to be almost exactly the two-force matrix S. So it was shown by Bapat that S is equal to tau, so the number of spanning trees, times omega. And well, this is more than enough to show that every non-trivial connected graph is twin-biased. So here's a sketch of the proof. So we saw that it's enough to show that beta I of G is non-negative for any I. Using the resistance distance, we are able to express beta I of G as a Rayleigh quotient of the Moore-Penrose inverse of the Laplacian times some matrix Zi. But then, well, L is symmetric positive definite because it's a Laplacian, so is L dagger, and so we are done because this expression is always non-negative. So you see that this is a quite powerful machinery. If I still have time, now I want to say something about how many graphs are paradoxical. So, well, first, a corollary of what I just said is that if we have a connected graph having at least 4 vertices and a pair of twin pendant vertices, so 2 pendant vertices adjacent to the same vertex, then G is always paradoxical, because if we add the extra edge connecting the 2 pendant twins, Kameny's constant increases. So the question is, how many connected graphs have a pair of twin pendant vertices? So I need to introduce rapidly some terminology now. So now A for me will be a class of graphs which is closed under isomorphisms. AN is the set of graphs in A having exactly n vertices. This expression here, Gn belongs U to AN, means that Gn is sampled uniformly at random from AN. And this is not a problem because AN is always finite. A has growth constant theta if theta is the inverse of the radius of convergence of the exponential generating function of A. So we will want in the result I will show you next that theta is finite and non-zero, which will mean that the exponential generating function converges in some fixed interval. So in a way, A does not grow too fast. Given two graphs G and H, AH of G is the number of times that H appears in G as a pendant appearance, which means as a pendant subgraph. And finally, if H is a rooted graph having root R, we say that H can be attached to the class A if for any graph G in A and for every vertex in G, if we take G union H and we add the extra edge VR, we still are into A. So it's somehow A is somehow closed under this operation. Okay, so and this is the result, the beautiful result I want to show. So this is due to McDermott, Steger, and Welsh. And it says that if A has a finite positive growth constant and Gn is sampled at random from An, and H is a rooted graph that can be attached to A, then for some positive constants, the probability that there are less than linearly many pendant appearances of H in Gn is less than e power minus nu n. So this means that with a probability approaching 1 as the order grows to infinity, there will be at least linearly many appearances of H in Gn. And this is again all we need to conclude. So almost all connected planar graphs are paradoxical. Okay, so well, to prove this, we consider the class CP of connected planar graphs. And H will be just the path on 3 vertices with the central vertex as the root. And the reason is that if we attach this, this path here to any graph, we obtain 2 pendant twin vertices. So exactly the construction we want. Okay, so first notice that CP has a finite positive growth constant. This was shown by Jimenez and Noy. And this is actually why we have to stick with planar graphs. So this is not true for generic connected graphs. They grow too fast. There are too many of them. But planar graphs are less, and their growth constant happens to be finite. Also, well, notice that whenever we attach a path to a planar graph, then we still obtain a planar graph. So H can be attached to CP. But then we can directly apply this theorem to show that if you have a connected planar graph on n vertices, and we let n approach infinity, then with probability approaching 1, we will have at least a pair of twin pendant vertices, and actually linearly many. And then we are done, because we know that if we have twin pendant vertices, then the graph is paradoxical. So this is all we need. Okay, so this was the end. Thank you very much.
Thank you, Lorenzo, for the nice talk. Can you remove the share? So let me check here if there are some questions. I can wait. So there is a question here for you, Lorenzo.
Hi, Lorenzo. It's Guy. Thanks for a nice talk. I have a question. So maybe you could share the screen again and show like slide 3, maybe, where you gave the definition of the Chemnitz constant. Was one of the first slides, at least. So yes, it's the on the third last bullet where you have MW, which is a constant vector, and that constant is Chemnitz constant. Apart from a 1. So I wonder, kind of intuitive question would be, since W is the result, is the stationary distribution of a Markov chain. So a Markov chain will converge to W. And the question is, how can you estimate Chemnitz constant? So then one may wonder if you can estimate Chemnitz constant by starting this Markov chain. And in each step, you compute a kind of estimate based on the estimate of W by multiplying by M, right? Mm-hmm. So in each step, you have a certain probability distribution, and it will converge to W. So I guess this sequence you get by taking M times the present probability distribution, that will converge to the Chemnitz constant by continuity, right? Apart from the 1, correcting constant 1. So don't you agree that would be a kind of iterative method to estimate Chemnitz constant?
Yes, I think this would work. I've never read this, yeah. So I think this is very interesting, and also I think Chemnitz constant also gives us the speed of the convergence.
Yeah, that's the question. Actually, if one could prove something on the speed on that convergence, so that would probably depend on the eigenvalue gap of the probability matrix, the Markov matrix, I guess. But also, I wonder if you could do things without computing M. So could you use the same Markov chain to estimate the elements in M and then estimate the product M times W iteratively? I'm not so sure about that one because it's maybe not the same Markov chain you need in order to estimate M. But what's your thoughts on that?
Well, so to estimate M, one way could be to use this recursive relation. So start with, well, any candidate for M and then let this equation act basically, and this should converge also to the real M. I'm not really sure how to do it starting from W. I'm not sure if we can do it for generic Markov chains, but maybe for random walks we can, because for random walks we have a characterization for M, if I remember correctly, in terms of the degrees, and since the degree vector is proportional to W, then we probably can compute it. Yeah, so I would say this, and also relating to the previous issue, there is a paper, I think, due to Kirkland and someone other, I don't remember, saying that Chemnitz constant gives us exactly the convergence rate if we start with any fixed probability vector P to W, if we have a primitive Markov chain. So Chemnitz constant in a way would be both the result of that process and also to measure the speed of convergence. So this is quite interesting.
Yeah, so I think it might be worth looking at this iterative method of estimating Chemnitz constant, which is different from the other approaches you talked about. I don't know, maybe. Okay, thanks.
Thank you very much.
Lorenzo, can you stop the sharing?
Sure.
Okay, so now we end the parallel session. So I want to thank all the speakers and of course the participants that were here. And thanks for the nice talks that allowed to this parallel session to be so good. So have a nice day now. So we end the session. Thanks.